Okay, I want to do exploration 1.3, number 6 here. So it says, graph shows the cross-sectional area, y, measured in square inches with our important units. So I'm going to actually write that up here. The y is area in square inches, or inches squared, is a function of the distance x from one of its ends, also in inches, important unit. Okay, so this is, we'll call it the distance from the end in inches. And what that means is if we look at this football over here and we go some distance x from the end, let's pretend this is like 4 inches here. The y value, the output, is the cross-sectional area, meaning if we cut a cross-section, just a circle from that football, and we try to calculate its area, that value will become the y coordinate. So if I say here is 1, 2, 3, 4 inches, and I cut that cross-section, then the cross-sectional area here looks to be 25 inches squared, or square inches. Okay, so that is what this graph is of. It's not the shape of a football because it's the cross-sectional area at each location. So if we look at x equals 2, for example, and let's just pretend that's 2 inches of distance that we go, well, then this cross-sectional area would be smaller. And if we look at our graph, this is 2, and this is 15. Okay, so this would have 15 square inches. And so all these little cross-sectional areas, if you put them all together, you can spread them out. That one should be bigger. But if you make infinite cuts in this football, you get infinite cross-sectional cross-sections, and then if you put them all together, you get the football back. And so it's just sort of imagining cutting the football into all these little pieces. And this is the area of each of those pieces. It is not the piece itself, right? This curve is not this. It is the area of each slice. Okay, so it says estimate the definite integral of y with respect to x. I think it would be better to have more information here, but from x equals 0 to x equals 12. Okay, I think this is the implication. This, pretty simple, you just count the boxes, get an estimate. So we'll count that as 10. Careful, each box counts as 5. This is 15. This is 20. This is 25. We'll use 25 again. And then we're going to use symmetry, right? We're going to utilize this. We're going to call this one box. Remember, it represents 5. We'll call this we'll call these two one box, call that 5. And we'll say this and this is kind of like 5, maybe a little bit more. So let's call it 6. And then this is, I don't know, you want to call that 7/10, so maybe 7. Add all those up. 5, 10, 15, 20, 25, 25, and then here we said we had a 5, here we had a 6, and here we had a 7. We were using symmetry, so we have to double whatever we get. Let's see, 15, 30, 50, 100, 111, 118. So 2 times 118. Hopefully my math is right. I get 236. Very importantly, though, the definite integral needs units. So what are my units? Well, in the horizontal x direction, my units are inches. In the vertical, the y direction, my units are inches squared. So each of these areas, okay, if we think of the area as being x times y, somehow it's the product of the x and the y, which means it is the product of inches by inches squared, and inches times inches squared is inches. inches cubed. And this is the area under the curve, right? Not just like area, it's the area under the curve. The accumulation of all that area under the curve is accumulating in the form of inches cubed. And what geometric shape do we know that's in the form of inches cubed? Well, that's three-dimensional, so that means we are in a three-dimensional shape. And three-dimensional is a measure of volume. So the definite integral, aka the area under the curve here, represents the volume of the football. And so we took the entire definite integral, so we took all the way under this curve. If we had, say, just taken this would be the area of half the football, or at 6 inches. Or sorry, the volume, my mistake. The volume when we get to 6 inches. If we wanted the volume up to 2 inches, we would just take the area under the curve up to 2 inches. Because paying attention to the units, inches by inches squared, allows us to know we are talking volume. If you accumulate cross-sectional area, right, the accumulation of all these areas, you kind of like stack them all on top of each other. And as they accumulate, you build out your football and you're creating volume. So this example shows that the definite integral can be used to accumulate anything. It doesn't have to be like a rate, like velocity accumulating to distance. It doesn't have to be a rate over time. It doesn't have to be like dollars per hour accumulating to total money. It can be other things, like you can accumulate areas, and those areas can accumulate into volumes. And this is why it starts getting to be really important to pay attention to these units, because maybe you know that cross-sectional area accumulates into volume, but maybe it's in looking at the units that this idea is revealed. Okay? So that's a great problem for introducing the fact that we can accumulate things that are not just rates. We can accumulate things like cross-sectional areas and other stuff. So that is what I want you to take away from this problem.